Hello, this is Dr. Jack Jackson. In this video, we're going to be talking about the cross product. So we're going to introduce this idea today. So recall that we have been talking about this idea of multiplying vectors, and we've seen in the previous two lectures how we've discussed two of the three different kinds of vector products. We talked about a scalar multiple, and we saw that we can multiply a scalar by a vector to get a vector. We accomplish this by multiplying each component of the original vector by the given scalar. The length of the resulting vector is the magnitude of the original vector multiplied by the absolute value of the scalar. If the scalar is positive, then the resulting vector and the original vector go in the same direction. If the scalar is negative, then the resulting vector and the original vector are in opposite positions. And of course, if the scalar is 0, then we get the 0 vector with all the components being 0. On a dot product, we saw that the dot product of two vectors in the same direction is a scalar. And it's found by multiplying all the corresponding components of the two vectors and adding these products. We also saw that we can see the dot product as the product of the norms of the two vectors times the cosine of the angle between the two vectors. It turns out this is the norm of the projection of the first vector in the direction of the second vector times the norm of the second vector, with a positive sign when the angle between them is acute and a negative sign when the angle is obtuse. The dot product is 0 if and only if the two vectors are perpendicular. Other words for perpendicular are orthogonal or normal. So in this video, we're going to be talking about the cross product. Scalar product with scalar times vector is vector. Dot product is vector dot vector is scalar. And the cross product, vector cross vector, is vector. Notice the different symbols for multiplication and the different type of thing that we conclude. So in this lecture, in this video, we will examine the cross product. The cross product is only defined for the cross product of two three-dimensional vectors. In contrast, the scalar product or scalar multiple is a scalar times any vector, no matter what dimensions. And dot product is defined as long as the two vectors have the same dimension. But cross product, we're only going to define if both of the vectors are three-dimensional vectors. And so the cross product of two 3D vectors is in fact a 3D vector. Now, as we did with the two previous types of products, we'll introduce the algebraic definition first and then show what the geometric interpretation is. However, realize this is backwards. The geometric interpretation actually came first, and then the algebraic definition was formed to fit what we wanted from the geometric interpretation. In the case of the cross product, it's a little bit more convoluted algebraic definition for this to work out. So it's going to be, even more important to realize that, it's not because somebody just came up with this formula, a cool way of multiplying vectors. They had a certain thing in mind they were trying to get to, and the algebra is just kind of what popped out of it. The dot product has something to do with the component of one vector parallel to the other vector, and the cross product has something to do with the component of one vector perpendicular to the other vector. Now, before we go any further, we're going to take a little sidebar and talk about the determinant of a 2x2 matrix. So if you have a matrix A1, A2, B1, B2, and then you take its determinant, which is written with these kind of like absolute values symbols, what you do is you multiply along this diagonal, A1 times B2, and then you subtract multiplying along this diagonal, A2 times B1. So for example, the determinant of the matrix 1, 2, 3, 4, 2x2 matrix, is 1 times 4, which is 4, minus 2 times 3, which is 6. 4 minus 6 is negative 2. So the answer is negative 2. Notice this is a single real number, a scalar. Could be positive, negative, or 0. Now we can also take determinants of other square matrices with 3 by 3, 4 by 4, and so forth. For our purposes of what we're going to be doing here today, we need to practice doing a 3 by 3 determinant. So here we have a 3 by 3 matrix and its determinant. The matrix is A1, A2, A3 for the first row, B1, B2, and B3 for the second row, and C1, C2, and C3 for the third row. Okay, and I'm going to show you a method called expanding by minors. So if we expand by what's this first row, what you do is you take A1 times the determinant of its minor. Well, its minor is remove the row and the column that A1 are in and look at what's left. Well, and leave them in their same sort of relative positions. So if you remove the first row and the first column, you're left with B2, B3, C2, C3 in a 4x4 or 2x2 4 number matrix there, or determinant of that. Then for the middle one, we have A2, and we're going to remove its column and its row. What's left? B1, B3, C1, C3. And the last one, for A3, we remove its row and column, and we're left with these four guys right here, B1, B2, C1, C2. Now, these are combined, these three things are combined, so notice it's A1 times that determinant of minor, then it's minus A2 times the determinant of its minor, and then plus A3 times the determinant of its minor. So it alternates signs, plus, minus, plus, like that. Well, now we know how to do these 2x2 determinants from the previous slide. So this is B2 times C3 minus B3 times C2. Remember, this minus is built in. And here we have B1 times C3 minus B3 times C1. And the last one we have A3 times, well, B1 times C1, B1 times C2 minus B2 times C1. And we can work that out. So let's look at an example. Let's take the 3x3 matrix and find its determinant. This matrix is 1, 2, -1 for the first row, 3, -2, 0 for the second row, and the third row is 4, -3, 5. So if we expand by that first row, that's 1 times the determinant of its minor, minus 2 times the determinant of its minor, plus a -1 times the determinant of its minor. The minor for the 1, eliminate that row and column, and you're left with -2, 0, -3, 5. If we take the row, the 2 there, eliminate its row and column, we're left with 3, 0, 4, 5 in that relative position here. If we eliminate the -1's row and column, we're left with these four guys here, 3, -2, 4, -3. So we have here -2 times 5 is -10, minus 0 times 3, that's 10, -10 minus 0 is -10. Here we have 3 times 5, which is 15, minus 0 times 4, so that's 15 minus 0 is 15. And for the last one, we have 3 times -3 is -9, minus a -2 times 4. -2 times 4 is -8, but the minus makes it plus 8. 10 minus 0 is -10. 15 minus 0 is 15. -9 plus 8 is -1. So then we have 1 times -10 is -10. -2 times 15 is -30. And -1 times +1, -1 times -1 is +1. Add these together, that's -40. Add one more, it's -39. So that's how you can compute a determinant of a 3x3 matrix. Now let me show you a slightly different way of getting to the same conclusion. Here's the way up here. Whoops, back up. Here's the way up here that we did it on the previous slide. Down here at the bottom, we can see another way of doing it. So start by just writing your matrix. Just drop the absolute value or determinant sign. Now recopy the first column and the second column after it like that. Start here at the top and the far left and go across and just multiply these things. 1 times -2 times +5, that's -10. 2 times 0 times 4, that's 0. -1 times 3 times -3 is 3. No, it's 9. +9. Add those together, -1. From that, we want to subtract the ones going across the other diagonal. Either start with the bottom left going up like this, or with this one coming down. So it's -1 times -2 times 4 is +2 times 4 is 8. 1 times 0 times negative 3 is 0. And 2 times 3 times 5 is 30. Okay, now just distribute this negative and 1 and add these together. So negative 10 minus 8 is, well, or I could do these together. I could do it different ways. I can distribute and then combine, or I can go ahead and work this out. So negative 10 plus 0 plus 9 is negative 1. 8 plus 30 is 38, and negative 1 minus 38 is negative 39. And you see, of course, the answer is the same as above. So either way of those works for doing the determinant of a 3 by 3 matrix. There's matrices are an interesting thing. We can use them. They form a kind of like a number system called a vector space, and we can work with those quite a bit. So you might have seen some matrices in your algebra classes or pre-calculus classes. You can use matrices to help solve equations, and there's like a whole course or more called linear algebra that you might take that deals a lot more with matrices and determinants and so forth. But right now we just kind of need it for one very specific purpose. And so let's take a look at that. And that is a way to help keep track of what turns out to be a kind of complicated, convoluted formula for computing the cross product. So here's one way to look at the cross product. If you have the vector A cross with the vector B, here's how we do that. So if vector A is A1, A2, A3, B1 is B1, B2, B3. So A and B are vectors. The A's with the subscripts and the B's with subscripts are just real numbers. What you do is you basically make a determinant here with the numbers in the first vector in the second row, and the numbers in the second vector in the third row. But in the first row, you put your unit coordinate vectors, I, j, and k. Remember, I is a vector just of length 1 pointing along the positive part of the x-axis. In other words, it goes from well, in 3D, it goes from the origin 0, 0, 0 to 1, 0, 0. And j is the vector that points in the straight up in the y or straight out in the y direction. That would be in 3D, that would be the point or the vector 0, 1, 0. And k is the vector 0, 0, 1 that points straight up in the z direction. All right, so we have this here. So what is this going to do? Well, if we expand by minors, we have the vector I times, well, eliminate that row and column. We have these four numbers in a determinant, A2, A3, B2, B3. Minus, now remember this is the one that's a minus, J, eliminate that row and column. This gives us A1, A3, B1, B3 for the minor. Plus K, and eliminate that row and column, A1, A2, over, and then B1, B2 for the second row. So now we just remember how this works. Well, this matrix, right, or this determinant is your I component, which I'm going to go ahead and write back with the this notation here rather than the I, J's, and K's. So that determinant is this right here, this determinant is here, and this determinant is here. So what do you get? You get A2 times B3 minus A3 times B2. Here we get A1 B3 minus A3 B1, but then we have to change the signs. So you end up with A3 B1 minus A1 B3. So that one in the middle is kind of backwards the way you work that out. And then K, this part will give us our third component, which is A1 times B2 minus A2 times B1. So there it is. There's the actual formula. I mean, the bottom line is this cross product of these two things is given by this formula. This, thinking of it as this determinant, is really just a way to help us remember that a little better. Okay, here's another way to get to the same number, same answer, that you might find better or might not. I don't know. So basically take A1, A2, A3, start with A2, forget the A1 for the moment, start with A2 and A3, then put A1 and then A2 across here do the same thing for the b's. Start with the second one, b1, b2, then b3, then b1, and then b2. Now, if you just go down the diagonals across this way, this gives you components in order, the three components of a vector, a2 times b3, comma, a3 times b1, comma, a1 times b2. From that, we're going to subtract the ones going the other way, a3 times b2, comma, a1 b3, comma, a2 b1. And of course, when you subtract those, what do you get? You get a2 b3 minus a3 b2, same as here. And then you get a3 b1 minus a1 b3. That's our middle term here, the cross product. And then finally, you get a1 b2 minus a2 b1 for the last one, and that's the same as this. So we see that that's an alternative way of doing it. Either one's just fine. You're going to get to the same way to do it at the end. You're going to get to the same number. The arithmetic that you end up doing is essentially exactly the same. So let's do an example. Let's find the cross product of 1, 2, 5 and negative 2, 3, 4. All right, so here's the expanding by minors way of thinking of it. We write our I, J, and K vectors. We write the first vector in the second row, 1, 2, 5, like that. And the second vector becomes the numbers in the third row of this matrix, negative 2, 3, 4. Okay, now we expand by minors. For the I component, we eliminate the first row and first column, and we're left with 2, 5, 3, 4. That determinant is 2 times 4, 8, minus 5 times 3, so that's 8 minus 15 is negative 7. For the J component, you get rid of that row and column, and you're left with 1, 5, negative 2, 4, but then we're going to do the opposite of it. So I did it this way, rather than doing the regular determinant and then distributing a negative 1, I just did it backwards. So the normal determinant is going down with upper left down toward the lower right. That one gives us plus that product, and going the other direction gives us minus. Then just do that backwards here. So start by going 5 times negative 2 is negative 10, and then minus the 1 times 4 this way. So negative 10 minus 4 is negative 14. Okay, now for the K component, we get rid of that row and column, and we're left with 1, 2, negative 2, 3. It's back to the normal way of doing it. 1 times 3 is 3, minus a 2 times negative 2. That's going to be plus 4. 3 plus 4 is 7. And so there's our vector. If we want to do it the other way we did it, what did I say to do? You start with the 2, and then the 5, then the 1, and the 2. So 2, 5, 1, 2. This one's going to be 3, 4, negative 2, 3. And then just multiply across here. These coming down. The ones with a negative slope actually are the pluses. The ones with the positive slope are the negatives. So the ones coming down from upper left to lower right, 2 times 4 is 8. 5 times negative 2 is negative 10. 1 times 3 is 3. And from that, we're going to subtract going the other way. 5 times 3 is 15. 1 times 4 is 4. 2 times negative 2 is negative 4. And then subtract, the corresponding components. 8, and this is minus 15, is negative 7. Negative 10 minus 4 is negative 14. And 3 minus a negative 4. Okay, 3 minus a negative 4 is 3 plus 4, and that's 7. And sure enough, that's exactly the same number I got going this way, the same vector. Okay? All right, you try this one. See if you can work it out yourself. What's B cross A? What is negative 2, 3, 4, and 1, 2, 5? I guess the question is, does that come out to be the same as what we just did or not? Regardless, work it out all the details by hand for practice, and let's see what happens. I'll give you a minute to do this one on your own. You'll need to press pause, work it out, and then come back. Press pause now. Well, I won't show you all the details here, but it turns out the answer is 7, 14, -7 for B cross A, but A cross B was -7, -14, 7. So is the cross product commutative? And of course, you can see from this one counterexample that the answer is no. But it turns out that the cross product, of course, is not commutative, but it's anti-commutative. If you reverse the order of the factors, then the magnitude of the cross product remains the same, but the direction is reversed. In other words, these two vectors, cross products in the two different orders, once you get one, just multiply all the components by -1 and you'll get the other one. So vector B cross vector A is the opposite of vector A cross vector B. And I did it for this example. Of course, one example is not a proof. You need to work this out in detail. So if you'll just replace this by, just like I worked out what the cross product was here, what happens with the cross product if you put the B's in the second row and the A's in the third row, and show in the end that it's just the opposite of what you get here. If you can show that, you'll have proved that result that I just said, right? That the cross product is not commutative, it's anti-commutative. So I'm going to leave that little proof as exercise. So see if you can work that out on your own. Okay, continuing on. So now we have this convoluted way of multiplying two 3D vectors together to get another 3D vector. But why in the world would anybody want to do it that way? Seems a little maybe convoluted, a little complicated. What does this mean geometrically? Now remember, as I said earlier, it's not that somebody came up with this, kind of crazy way of multiplying two vectors together to get another vector and then said, well, oh, that's kind of cool. Now what can I do with it? It's actually the other way around. They came with a certain geometric meaning that they'd like to have, and then they showed that it happened to be this, a little bit more complicated formula, but a formula that we can do nonetheless. So in order to better visualize what's going on, we're going to use this app that I created in GeoGebra. And this particular app, we're going to restrict our attention to two 3D vectors, but these vectors are in the XY plane. You'll be able to control the vectors by these sliders or these input boxes here. But notice they only control the x and y components. The z components are 0. That keeps them down in one xy plane, and that way we can focus our attention on what's happening in that plane. And that just makes it easier to see what's going on. Now, on the one hand, that might seem like a huge restriction, but it's really not that big of a restriction because no matter what we have, any two 3D vectors, you can put them sort of tail to tail, and they will form there will be only one plane that contains both of the vectors, unless they happen to be parallel. So if you got two vectors that are not parallel, you can do that, and there's just one plane. It may not be the xy plane, but it may be some plane. And so the general situation is kind of similar. The plane may be, slanted at some angle or something, and not just the xy plane. Okay, so let's take a look at the app now. So this is going to, if you click on that link or type that link in your web browser, you'll get to this thing here. It's already opened up in the app, so that's good news. So there we have some vectors. Again, I can change the x component here. I can change the y component here. Right now that makes them all integers, but you can actually put in, fractions or something there if you want. Okay, so there's a couple of vectors. Some information is shown over here. This is the angle between them. This is telling us what that vector is. This is the length of that vector from D to E is the norm of W. And if I click right here, there's the magnitude and direction. Now this direction is the green, indicated by the little green angle symbol from the horizontal to this vector W. And there it is, the norm approximately, of course. What is it really? It's the square root of 3 squared plus 2 squared plus 0 squared. That's 9 plus 4 plus 0 is 13 square root. So it's square root of 13 is exactly what it is. So this should be approximately the square root of 13. And then that angle then would be, probably expressing it as an arc cosine would be the best way to do that as an exact value, but as an approximate value, here's what it is in radians. You could, of course, get a degree approximation too as well. So let me not show that. You can also turn on the components there and, of course, see that it's going right 3 and up 2. And the same way for the other. You can see it's going to the right 10 and down 4, or out a distance of 10.77 approximately at this angle of 5.9 radians. All right, so let's start by reviewing the dot product, okay? Because this application actually is not just for cross products, it's for cross product and dot product. Now, some of this we've already done in the previous one. So here, we can see the dot product worked out. Here's the general definition of the dot product. So W dot V is going to be 3 times 10, shows you right there, it's 30, plus 2 times negative 4, that's negative 8, and 0 times 0 is 0, so 30 minus 8 is 22 for the dot product. Now we also saw earlier that the dot product was also the norm of W times the norm of V times the cosine of the angle in between. There's the norm of that distance across here is the norm of W. And if we do this, there's the norm of W. There's the norm of V. So notice those two numbers are the same as these two numbers. And then the angle between is this 0.9685 radians approximately. So we do the cosine of that angle, multiply by those two norms, and we get the answer. I actually did these two. I did the norm of V times cosine of the angle and did that 6.1. Now, why did I do that? Well, that is something to do with the projections. So if I project, let's see, here I'm projecting onto the, let's see which one's which. The green vector is W and the blue one is V. So here I'm projecting onto W and getting a component in that direction, which is this light blue thing. And then we have a normal component or a perpendicular component going this way. So we can think of this vector here, this blue one, D, as being the sum of two vectors, one going in the direction of W and then one going perpendicular to that. Now it turns out the perpendicular component has nothing whatsoever to do with the dot product, but it does have but the parallel component does have something to do with the dot product. You're just multiplying that length of that vector times the length of the green vector here. So if you notice, that makes an area here, and I just took this light blue vector, the projection there, and rotated it around to get this side right here. There's its length, 6.107, which is the norm of V times the cosine of the angle theta between them. Multiply that by the length dE, the length of vector W, and you get this purple area here. 22 is the dot product. Now, the cosine of an angle could be positive, negative, or 0, so the dot product is a scalar, which could be positive, negative, or 0. Okay? So that's kind of interesting. Now, let's compare and contrast that to the cross product. Okay? So, look what we're going to change. Actually, we don't change a lot in one sense. We're going to change, instead of having an area like this where one side is the parallel component and the other one is this vector W, what we're going to do for the cross product is we're going to see an area that is, again, the same as the vector here, but the other side is formed by the perpendicular component. Okay, well that's not that much of a change. I mean, that's kind of a nice kind of a change that we might expect to do. Okay, so it turns out, of course, that the component there from this right triangle here, if theta is the angle between, um, is well, the sine of that angle is opposite over adjacent, opposite over hypotenuse, excuse me. So that would be this size of this component here over the norm here of the blue vector, that's v. Okay, so if we take the norm of v times the sine of that angle, we'll get the length of this black normal vector right here. It's a right angle right there. Well, if we do that, we take v, the norm of v times the sine of this angle in between, we get about 8.8752. So the 10.7703 here is the length of the vector v. That's the length of the blue vector. It's that length. Okay. And then when we project it on here, we get a part going in the same direction. That's this light blue vector. And a part going perpendicular, which is the perpendicular or normal component, orthogonal component, which is right here. Multiply the norm of v and the sine together, sine of theta, you get the 8.875. That's the length of this black vector, which you can see is the same as here. And just bring that across with this side here, and we get another rectangle. Well, that 32 turns out to be the norm of the vector that we're wanting. So that the norm of the cross product turns out to be the area of this rectangle. Now, it also turns out to be the same as the area of this parallelogram, right? Now, think about it, this parallelogram. What can we do? We can take, let's see, we want to think of, if we think of the green vector as being the base, then the height is the perpendicular distance from that side to the parallel side here, which is the black vector here. So you remember that this parallelogram and this rectangle have the same area. As you can see, it's figured it out here in the program. It's 32, which is this magnitude here. And of course, the area of a parallelogram is base times the height being this perpendicular distance between these two bases, same as this rectangle. So what is it again? Compare and contrast. The dot product is the area, well, it's a signed area of a rectangle formed by the one of the first vector, let's say, and the component of the second vector in the direction of that. So it's just multiplying that length times that one here, where it's positive if these components here, if these projections, the blue projection is in the same direction as the green one, and it's negative if they're opposite. And so that gives us the dot product. This is a scalar. Cross product, well, the magnitude of it at least, is taking that perpendicular component times the length of this vector here, and that gives us that area. And by the way, for angles theta between 0 and pi, which is how we measure the shortest or smallest possible positive angle between them, then that sign is always positive. So that gives you, that means norm of w times norm of v times sine of theta will be a positive number, which of course, or 0, which of course is exactly what happens all the time when you do a norm. So we can see that it's a nice, just sort of variation on a theme of what we saw with the dot product, if we think of it that way. And we could also think of it nicely as this area of a parallelogram, where the two sides of the parallelogram are your two vectors. So we can think that as a nice parallelogram area. Okay, so let's go back to our slideshow, and this is just going to be some static pictures of what we just saw. So here is once again the dot product. different example here, but because I changed the numbers here. There's the definition. Here's the example worked out. Again, I've specifically picked these vectors to be a 0 z component just so that all the graph will be down in the xy plane that we can look at. And we can see that here it is worked out by the definition. Here it is by the alternative formula that you get the same thing. And we can see it visually as the area here. It's either going to be a signed area at least, positive or negative. 1 times this area, in this case, the area is positive. So the absolute value of the dot product is the area of a rectangle with the second vector as a side, and the other side is the parallel component of the first vector in direction of the second. Or let's see, what did I say? So this could be, actually I did this differently, didn't I? Okay, it doesn't really matter because it's actually commutative, but let me make sure the statement down here matches the picture. So the absolute value of the dot product is the area of a rectangle with the first vector as a side, and the other side is the parallel component of the second vector in the direction of the first. Now, let's just change a couple of words here, and we'll get the cross product, or at least the magnitude of the cross product. So remember that the dot product is a signed area produced by multiplying the component of the, let me go ahead and change this to match what we just said too. So let's say this again, the signed area produced by multiplying the component of the second vector parallel to the first vector by the magnitude of the first vector. It turns out it's the product of the two norms and the cosine of the angle between the two vectors. And notice that the cosine is positive for acute angles, negative for obtuse angles, and 0 when the vectors are perpendicular. So A dot B, vector A dot vector B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle. Now we just change a couple of things here. We just change the word parallel to perpendicular, cosine to sine, and dot product to magnitude of cross product, and we change cosine to sine in the formula here. Everything works out right. So the magnitude of the cross product is the area produced by multiplying the component of the second vector perpendicular this time to the first vector by the magnitude of the first vector. Or it's the product of the two norms and the sine of the angle between the two vectors. Notice that sine is always positive or 0, and it'll be 0 when the vectors are parallel. So the cross product is going to be the 0 vector when the vectors are parallel, same direction or opposite directions. So the norm of the cross product is the magnitude of A times the magnitude of B times the sine of the angle theta between the two. So if you think about it, this is a real natural way to get to the cross product. Okay, continuing on, we'll look at the slides here. Here's another static picture from the dot product cross product thing that we were looking at again. Again, the magnitude of the cross product is the area of a rectangle with the first vector as a side here, and the other side being the perpendicular component of the second vector projected onto this one here, the perpendicular component, which is this black one. Of course, it's also, as we saw, a parallelogram area, which I'll show you in the next slide. It's the area of that parallelogram with the two vectors as the sides. Now, as far as this goes, it doesn't really matter whether you're doing, the order. The dot product is the same either direction. If you sort of switch the first and second ones, when you get back here, let's see here, you'd get a different rectangle, but it would have the same area. One side would be this, and then you'd get you get another side, that would be of the projection here. This would come down here. A different shaped rectangle, but with the same area. But of course, the dot product is commutative. As far as the magnitude of the cross product is, that part is commutative, just the magnitude, not the cross product altogether. It doesn't matter whether you're thinking about which vector is going on which one. Again, you would get maybe two different rectangles there, but they would be with the same area. You'd still get something equivalent to the area of that parallelogram. So that doesn't matter. But what matters is we do get the vector's direction being different, in fact opposite, depending on whether you do W cross V or V cross W. Okay, and so let's continue taking a look at that. So there it is, visualized as a parallelogram. Now, so what did I do? I said the magnitude of the cross product was this norm of A times norm of B times sine of theta. Well, I said that, but let's actually prove that. So this is the proof. It's to be honest, it's a little messy here, so just bear with me. Okay, it's not hard. It's just tedious. A lot of tedious algebra involved here. And what are we going to use for things? Well, we're going to use this fact that the dot product is cosine of theta is A dot B over the two norms, product of the two norms. And we're going to use this basic Pythagorean identity from, we know sine square of theta plus cosine square of theta equals 1. Solve for sine of theta. Sine of theta equals the square root of 1 minus cosine square of theta, at least when sine of theta is positive, which it is for angles between 0 and pi. And we're going to use some definitions in component form and a whole bunch of just tedious algebra here. So just bear with me here. So let's start with the norm of A times the norm of B times sine of theta. And this is the way they would actually have done this the first time. They wouldn't have said, oh, let's figure out this matrix thing and determinants to figure out a cross product. No, they would say, hey, we want something whose magnitude is given by this thing here. What we really want is we want norm of A, norm of B times the sine of theta. What does this have to do with the components of A and B? Well, sine of theta is the square root of 1 minus cosine square of theta. That's just using a basic Pythagorean identity. Now we can replace cosine theta with A dot B over the two norms. Okay? So if we square all this out, you get A dot B square over norm of A square, norm of B square. And I want to get a common denominator, so think of 1 as norm of A square times norm of B square over the same thing. All right, now let's see. We get a common denominator. In the top, we have norm of A square, norm of B square minus the dot product square. That's under the square root. And then we can think of just norm of A square times norm of B square in the bottom, and then put the square root just over that. Well, the square root's going to cancel the squares to just be, well, here it is. And that's going to cancel the squares. Let's just look at that part. To be norm of A times norm of B, since those are positive, and it cancels with this numerator. So here's some good news. This part in the beginning is now gone when you get down here. All right, now here's the bad news. We got to work out this part under the square root. So the norm of A is you take A1 squared plus A2 squared plus A3 squared, square root that, but then the square cancels that square root. Now it's still under this big square root, but the square and the square root from the norm cancel each other out, so we get this. Similarly, we get the norm of B squared is B1 squared plus B2 squared plus B3 squared. And from that, we're going to subtract the dot product, which we know algebraically is A1 times B1 plus A2 times B2 plus A3 times B3, but it's that dot product squared. All right, here's where it gets kind of tedious. So now we want to multiply these two things. We can write one above the other and use kind of a long division, a long multiplication algorithm or whatever, but basically it's just repeated applications of the distributive property. We take the b1 squared times each term here. So it's a1 squared times b1 squared, a2 squared times b2 squared, a3 squared times a b1 squared. And then multiply each one of these by b2 squared. That gives you this one, a1 squared b2 squared, a2 squared b2 squared, and a3 squared b2 squared. Plus, then do the same thing for the third one. This has your a1, a2, and a3 squared each times b3 squared. All right, that's this first product. For the second one, do the same thing, except instead of two different polynomials here, you have this this a1b1 plus a2b2 plus a3b3 times itself. So let's see what order I did. And then it's minus out here. So all of the terms from this next one are going to have a minus. See that? So if we start with the a1b1, let's see, how did I start? Yeah, I started with a1b1 times each one of these three. Well, it's a1b1 times a1b1 is a1 squared b1 squared. a1b1 times this one gives you an a1, a b1, an a2, and a b2. There it is. Of course, it's minus because of this. And then the a1b1 times this one gives you an a1b1, a3, b3. There it is. And then a2 times a2, b2 times each one of those gives you these three terms. This one, and this one. And then, let's see, where am I? Yeah. So the first one, the a1, b1 times each of these three gives you this term, this term, this one. The a2, b2 times each of these three gives you the next three terms. That would be this one, and this one. And the third one would be a3, b3 times each of these three gives you the last three terms. Okay, yeah, yuck. But anyway, man, it's massive. Okay, so now the good news is it starts to get a little better. Okay, so it turns out that all the ones that are just squares here, they cancel out. So see if I can kind of show that to you. A1 square, B1 square here cancels with, there's the minus version there. The this version, A2 square, B2 square cancels with that one. And A3 square, B3 square cancels with that one. You're left all these others with squares here, where they're different denominators or different subscripts. Now, the ones that are left over here actually collect up in pairs. You may have to reorder some of the things, but for example, this one has an A1, B1, and an A2, B2. There's it is. There's a matching one right there. See those two? They're the same, so you get minus 2 of those. The same thing happens for the others. There's one A1, B1, A3, B3, and the matching one there is right here. There it is. So there's two of those. And the last two would be this. Let's see. 2, 3. There it is, that one and that one. And those two match up to give us that one. All right, well, still quite a bit of mess. But it turns out if you group things correctly, some nice things happen here. So let's take the ones that just have the 2's and 3's. So here's A2 square B3 square, and here's A3 square B2 square. If you look, you can find those up here. That's this one and this one. And let's do the ones that have just 2's and 3's. Put that one in the middle. And I want to think of it as 2 times this, okay? And I'm going to group those three together. And I'm going to do the same thing for the other. I'm going to put the ones that have just 1's and 3's together. So that would be, say, this one and this one together, and put that with this one in the middle. And the last one, I'll put the ones that just have 1 and 2 for subscripts. Put that one and that one and that one in the middle. It gives us this. Now, by grouping them these ways, each one of these three can be thought of as a trinomial square. See, that's a square of A2B3. That's a square of A3B2. And the middle is these two multiplied together and doubled. So when we factor that, it factors as a binomial squared. And that's true for every one of these. This one is A1B3 square, that's A3B1 square, and multiply and double, you get the middle term. And similarly for the last one. Okay, well, whew, that's a lot of arithmetic, a lot of algebra going on there. None of it was really hard, but quite tedious. All right, so let's keep going here. Well, somebody did this, right? Somebody said, "Oh, we'd like to have norm of A times norm of B times the sine of the angle. What does it have to do with A, B, and the components of A and the components of B?" Well, it's this. And then they started looking at that. Said, "Boy, that looks a lot like the norm of a vector, right? Something square plus something square plus something square, and then square root." Well, that would be the norm of the vector if the vector had this for the first component, this for the second component, and this for the third component. And so that tells you, oh, if I can just define a vector with those three components, then that would be the norm of that vector. So we define the cross product that way. So see, it's not because they define the cross product that way and then it turns out to be this. It's more the other way around. We're looking for something where the norm, we want norm of A, norm of B times the sine of the angle, and it turns out to be this, crazy formula. Well, let's let that crazy formula be the cross product. Not so crazy after all. It actually is something important. Okay. Now let's look at something about the direction of the cross product. Okay. Now right now we're in the xy plane, so the z coordinates are 0. So vector A could be A1, A2, and then 0. Cross that with B1, B2, 0. Here's one way to look at it over here. Take A2, 0, A1, A2, and then B2, 0, B1, B2, and do it like this. So you get A2 times 0, 0 times B1, those are always 0, and you get A1 times B2. Subtract from that, 0 times B2 is 0, A1 times 0 is 0, and A2 times B1 is here. So you get A1 B2 minus A2 B1. Of course, that looks exactly like a little determinant. But these are 0. So the most important thing is notice that both of these guys are 0. So the vector that we have, where is it? It's either pointing straight up or straight down in the z direction. It's some multiple of the unit vector k, right? So it's either straight up or straight down out of the plane. So notice that's perpendicular to every vector in the xy plane, including vectors A and B. Now reversing the order to B cross A is not going to change the magnitude, but it's going to reverse this so that perpendicular vector is going to point straight out of the plane, either straight up or straight down. Okay. Now there's two ways that this works out. It turns out that the way it works is by the right-hand rule. If you point your fingers of your right hand along the vector A and rotate them the smallest way you can to get to vector B, your thumb is going to point in the direction of A cross B. And of course, if you do B cross A, you're rotating the other way, and so the vector points the other way around. You might think if you're left-handed, you go, oh, there you go, right-hand rule again. Why not the left-hand rule? Well, here's another time that it's not, the world is not set up for folks like us left-handed people. Well, actually, you got an advantage if you're left-handed, because if you're thinking of the cross product, you can pick up your hand and move it around without ever picking up your pencil, where right-handed people have to set their pencil down and figure it out and then pick your pencil back up. So actually, left-handed folks have a little bit of advantage here. Okay, now it turns out that this is not a coincidence and not true just for vectors in the xy plane. No matter where vectors A and B are, even if they're not just in the xy plane, they're in some plane together. And the two vectors basically determine that plane. And it turns out that the cross product is always perpendicular to that plane and in the direction of the right-hand rule. And I'm going to show that it is perpendicular by proving that the cross product in general is perpendicular to both vectors A and B. So the cross product of A and B is A1, A2, A3 cross B1, B2, B3. And as we saw earlier, that's given by this formula, which now we kind of know why it turned out to be this. Well, how do we show two vectors are perpendicular, also known as orthogonal or normal? Well, the dot product has got to be 0 in that case, and here we're going to do that. So if we take this cross product given by this formula right here, and we do A dot that, so let's see what happens. We do A1 times this, so that's A1 times A2B times B3, minus A1 times A3 times B2, plus, we'll do A2 times these here, so that's A2, A3, B1, minus A1, A2, B3. There it is. Plus A3 times this last one. That's A1, A3, B2 minus A2, A3, B1. Now notice I've kind of color coordinated them this time so you can see this, the canceling. The two red pieces cancel, the two blue pieces cancel, and the two black pieces cancel out. So sure enough, you get the scalar 0, and so that tells us that vector A is perpendicular to the cross product, or the cross product is perpendicular to vector A. And different slight calculations, but basically same idea. We could do the same thing for vector B. Here's B1, B2, B3 crossed with this cross product, or dotted with this cross product. So B1 times this distributes the B1, so it's A2, B1, B3, A3, B1, B2. Then we plus, you do the B2 times this one, A3, B2, B1, B2. Let's do it that order. Minus A1, B2, B3. There it is. Plus B3 times this one, so that's A1, B2, B3 minus A2, B1, B3. And again, the red ones cancel, the blue ones cancel, and the black ones cancel. So once again, we get 0. So the dot product of B and the cross product is 0. So the cross product is perpendicular to vector B. So in the end, what do we have? We have the cross product is a vector that's perpendicular to both of the original vectors, and its magnitude is the area of that parallelogram with those two vectors as the sides, and that area is given by the norm of A times norm of B times the sine of the angle in between. And of course, then we have this kind of crazy formula right here for the dot product, for the cross product, to make all that work out. Now, one nice thing about this being a vector is it is a normal vector or perpendicular vector, and sometimes we'd like to get our hands on a perpendicular vector sometimes. So see if we can solve this problem. Find a unit vector normal to the plane containing the following three non-collinear points. Now remember, if you have 2 points, that determines a line, exactly one line through those 2 points. 3 points determine a plane if they're not collinear. So in other words, if they're not all in a straight line, there's exactly one plane containing these 3 points. See if you can figure out how to do this one on your own, and then if you can figure it out, come back and check your work here. Press pause now. Well, as you might expect, we're going to make some use of the cross product. So first we're going to make a vector going from A to B and from A to C. So from A to B, it's basically delta x, delta y, delta z are your components. So it's -2 minus 1 is -3 for the x component. 4 minus 2 is 2 for the y component. And 3 minus 5 is -2 for the z component. We'll call that vector, it's the vector from A to B, we'll call it vector v. And the vector from A to C is, let's call that w. It then would be 2 minus 1 is 1. -3 minus 2 is -5. And 3 minus 5 is -2. So there's vector w. Now just find the cross product between vectors v and w. And I did it in the order v, then w. So here it is in sort of the determinant form. And so either way, it helps to remember it. There's, we could also do it a couple other ways, but if you think of it this way, the I component is given by the determinant for these 4 guys. So 2 times -2 is -4, minus a -2 times -5. So it's -4 minus 10 is -14 for the x or I component. For the j or y component, we get rid of this row and column, so we're doing a determinant here, but remember the one in the middle is backwards, so we start by doing positive this way. -2 times 1 minus goes this way, minus a -3 times -2. So that's 2, negative 2 minus 6 is negative 8 for the the j component or y component. For k, we get rid of this. We're just doing the determinant of these four. So it's negative 3 times negative 5 is 15 minus 2 times 1, that's negative 3. 15 minus 3 is 12. And so there's the cross product. So that is a vector that is normal or perpendicular to the plane. We want to make it a unit normal vector. N is the vector we're looking for. We just make this into a unit vector by dividing it by its magnitude, by its norm. So we're doing the cross product divided by its norm will be a unit vector perpendicular to both of these two vectors, and hence perpendicular to every vector in that plane. So the norm of this would be, well, might as well drop the negatives. 14 squares, same as negative 14 square. 8 square and 12 square add up in square root. So those squares are 196, 64, and 144 for a total of 404. I can factor a 4 out, so we got the square root of 4 is 2, and then you're left with the square root of 1. Distribute that, the 2 cancels this down to a negative 7, a negative 4, and a 6, and they all have the denominator of square root of 101. And so that is a normal vector. There's actually two of them. There was two answers to this problem. The other answer is just the opposite of this. So it'd be positive 7 over square root of 1, comma, positive 4 over square root of 101, comma, negative 6 over square root of 101. And of course, I would have found that one directly had I started with W cross V rather than V cross W. So either way, you'd end up with those two unit normal vectors. It just said find one, so there it is. There's one of them. And that particular vector is going to be pointing it in the direction of the right-hand rule by starting your fingers, pointing them from A to B along V, the vector V, rotating the quickest way we can to get to C along to the vector W, and then use your right hand, and the thumb then will point in the direction of this vector N right here. And once again, that N has a norm of 1. All right, so there we go. A little longer than my normal videos, about an hour in on this one, but that gives us a introduction to the cross product, proved all the basic things about it. We were able to see it algebraically, see it geometrically, have a couple of different formulas on how to get there. We've got the well, kind of one algebraic formula how to get there. We have also an alternative formula how to get to its norm, given the angle between there. And we saw how we can interpret the characteristics of it, both its magnitude and direction. Notice it is a vector for the answer. Along the way, we got to review a little cross product as well. So there we go. So now you can use dot products, cross products, and scalar products all now.